Terzaghi Lecture. It's the 40th Terzaghi Lecture, and it's going to be presented by Professor Harry Poulos. The Terzaghi Lecture, as you know, is the most prestigious award that is given by ASCE in conjunction with the Geo-Institute. And it is with great pride that we provide this lecture and presentation to you tonight, and that we get the opportunity to honor our 40th Terzaghi Lecturer, Dr. Poulos. And I'm also pleased to announce that the president of ASCE, Pat Galloway, is with us here tonight. And Pat would like to say a few words to you this evening about this event. Thank you. Pat, welcome.
Thank you very much, Sandy. You know, it is indeed a pleasure to participate in this most prestigious and scholarly Terzaghi Lecture this evening. It was instituted by the ASCE Board of Direction in 1960, and the Terzaghi Lecture was established by the now Geo-Institute in honor of Karl Terzaghi. Annually, the Geo-Institute Board of Governors recommends a distinguished engineer to deliver the Terzaghi Lecture. The 40th Terzaghi Lecture is Professor Harry Poulos, Senior Principal with Coffey Geosciences in Australia. And I must say, it's fun to see an Australian. I spent a lot of time in Australia. We have a firm down there, and I am very excited that we get to see someone and broaden our global perspectives in what we're doing with our awards and our awardees. So I congratulate you on that. Our speaker tonight has certainly shown the expertise, innovativeness, and commitment that matches the example set by Karl Terzaghi and other distinguished recipients of the renowned lectureship. I would like now to ask Dr. Poulos to join me at the podium. Dr. Poulos, in recognition of your significant contribution to the development and practical applications of geotechnical analysis to deep and shallow foundation, I would like to personally, as the president of ASCE, congratulate you for your outstanding accomplishments as this year's Karl Terzaghi Lecturer. I look forward to your lecture on pile behavior, consequences of natural and construction imperfection. I also want to thank you for your leadership, your dedication to the profession, and your ability to share with us this wonderful evening tonight. Sandy, I'll turn the program back over to you. Thank you very much, Dr. Poulos.
Thank you very much, Pat. It's a pleasure having you here with us this evening. At this time, I would like to invite Arlen Rippey to the podium. He is the incoming president of the Geo-Institute. He's currently Senior Principal Geotechnical Engineer with Kleinfelder in Beaverton, Oregon. And I would just like to say that Arlen has a tremendous track record in service to the geo profession and to ASCE, and he's just going to be a wonderful president for the Geo-Institute. And I'm very, very pleased to have him following here behind me. And Arlen, so congratulations. I'd like to pass you officially the gavel. So just 1 minute. I got to go get it. So it is now official. You are the president of the Geo-Institute. It is my honor to present Dr. Harry Poulos. This prestigious annual Terzaghi Lecture is one of the highest honors that can be conferred in the field of geotechnical engineering. And it is with very great pleasure that we give it to Dr. Harry Poulos, who is a friend and colleague to many people who are out there in the audience. Professor Poulos is currently Senior Principal and Chairman of Technical Development with the consulting firm of Coffey Geosciences. He's Emeritus Professor at the University of Sydney and Adjunct Professor at Hong Kong University of Science and Technology. Over his career, Professor Poulos has attained the highest level of excellence in research and engineering practice in the field of geotechnical engineering and foundation engineering in particular. His work in pile foundation analysis and design has enabled the world's geotechnical specialists to have greater understanding of soil structure interaction, which is one of the most challenging problems that faces the geotechnical profession. Harry was born in Australia in New South Wales shortly after his family of Greek heritage moved to Australia. Harry received his undergraduate degree from the University of Sydney in 1961, and he was awarded the PhD degree in 1965 for his dissertation on the settlement of clay soils. He was also awarded a higher doctorate in 1976 for his collected papers. His was only the second higher doctorate in engineering at the time, representing a very high honor in the University of Sydney. In the period from April 1964 to January 1965, Harry gained early professional experience working as a consulting engineer with McDonald, Wagner, and Priddle. He returned to the Department of Civil Engineering at the University of Sydney in 1965, where he has held positions of lecturer, senior lecturer, reader, professor, and head of the School of Civil and Mining Engineering, director of Postgraduate Civil Engineering Foundation, and founding director of the Center for Geotechnical Research. Since June '89, he's worked as a consultant for Coffey, but at the same time, he has also held a professional appointment with the University of Sydney. Professor Poulos has been in great demand as a lecturer and has received numerous invitations to deliver lectures throughout the world. His personal contributions to teaching and research and design in geotechnical engineering are enormous. He's an author of 3 books, more than 250 technical papers in geotechnical engineering, with a large number dealing with his favorite subject of pile foundations. These days, he's acknowledged internationally as one of the leading practitioners in the design of pile foundations, but his practical expertise has always been founded on solid theory. He's been involved in over 300 major projects in Australia and in overseas. His contributions have been recognized formally by his peers, and he was awarded the 1989 Ranking Lecture as Fellow of the Australian Academy of Science and Australian Academy of Technological Science and Engineering, a Fellow of the American Society of Civil Engineers, an Honorary Fellow of the Institution of the Engineers of Australia. He received the Warren Prize and the Warren Medal of the Institution of Engineers in Australia, and the State of the Art Award by the American Society of Civil Engineers. He's been invited to present the Davis Memorial Lecture, the John Jaeger Memorial Award to the Australian Geomechanics Society. He's given the Schiffman Lecture at Cornell University, the Arteman Lecture at the University of Florida, and the inaugural Athene Geotechnical Lecture in Greece in 2000, as well as the 8th Spencer Buchanan Lecture at Texas A&M University in 2000. In 1993, he was made a member of the Order of Australia for his services to engineering, and in 2003, he was awarded a Centenary Medal by the Australian government for his services to science and geotechnical engineering. Recently, he was selected as the Australian Civil Engineer of the Year for 2003 by the Institution of Engineers of Australia. Harry also serves as an appointed board member of ISS MGE, and that period of service was from 2001 to 2005. He's been a member of editorial boards for 6 leading geotechnical journals. Harry's list of projects and achievements is large and very, very impressive. His Australian colleagues tell me that he is well known in the profession. It is well known in the profession that if an Australian structure is founded on piles, that it is likely that Professor Poulos has had some involvement, if not directly, certainly through involvement through his large number of students that he has taught and influenced over the years. Recently, I had the pleasure of speaking with 2 of Harry's longtime colleagues and friends. He's been described as a person of great dignity, civility, and calm self-assuredness. These are qualities that Harry has carried with him without faltering throughout his life. He is quite simply the quintessential gentleman. As most of you are aware, Professor Poulos has had a very long association with the University of Sydney. He first entered the university as a student in 1957, and he graduated with first-class honors and degrees in civil engineering in 1961. His friends and his colleagues recognized him very early on in his career as someone with unique and outstanding talents. And if we could, I would like to just put up a picture here of Professor Poulos from his years. Now you can see that he was a trendsetter even in the 60s. You know, he's got the backwards hat. He was a very cool guy. Obviously, the most likely to succeed, Harry, and you have certainly done that. So we're very proud of you. And I'm sure your classmates from that era are very proud of you as well. His friends say that his appetite for work and his immediate grasp of the task at hand was awesome, truly inspiring awe. And he has a truly remarkable memory. Harry also has a passion for collecting books and recorded music, but particularly books. He has a huge personal library where he's collected over many years, and it's told that he had to add on extensions to his house just to make room for all of these books, although he would always claim it was for his growing family, but everybody knew it was for his books. Some of his collections are quite obscure. For example, he's probably the only person in Australia with a coffee table book entitled The Grasses of Wyoming. His friends tell me that was one of his bargain buys. Along with his love of books comes what his friends describe as an encyclopedic mind on many subjects. A question such as, Harry, do you know if anyone has published on this particular subject? Being followed by sights of Harry dashing around his office and pulling out relevant titles or rattling off a list of possible leads to the technical literature. Apparently, Harry is also quite knowledgeable in sports, and he's himself excelled at the game of cricket and golf, and even served as a soccer coach. On the downside of this, however, Harry's academic mind is often turned to detailed analysis of past sporting performances and results, and this is much to the upset, I think, of maybe some of his colleagues and friends. Harry is a devoted family man. He and his wife, Maria, have 4 children and 7 grandchildren. Please join me in welcoming Professor Harry Poulos in his 40th Terzaghi Lecture entitled Pile Behavior Consequences of Natural and Construction Imperfections. Professor Poulos.
Thank you very much, Sandra, and thank you, ladies and gentlemen, for coming here tonight to listen to this lecture. I am indeed greatly honoured to be invited to give this lecture, which is, of course, named after the founder of our discipline, and I recognise that I follow in the footsteps of many of the leaders of our profession, and so I am extremely grateful to the Geo-Institute for this singular honour. In my academic career, I had the luxury of being able to deal with ideal situations and looking at the behaviour of foundations and pile foundations in particular under ideal circumstances. As a practitioner and a consultant, that luxury unfortunately has dissipated. I've had to deal with the harsh realities of real geotechnical life and the fact that the real life has imperfections which the academic life does not. So what I want to try and do in this lecture is really to look at the consequences of the realities of life, and in particular the imperfections that arise both from natural circumstances and from circumstances which arise from construction operations. So what I want to do in this next hour or so is to firstly, very briefly, look at the sources of imperfection, how we can analyse those in a pile-soil interaction analysis, and then look specifically at a number of natural or geological imperfections and their effects on pile behaviour, then to look at the influence of construction imperfections, and finally to try and suggest ways in which we can cope with the consequences of those imperfections. And because of time, I may be rather brief in my description of a number of these case histories, so forgive me please for that. Usually we start with a definition of what we mean by imperfections. And if I look in the dictionary, I find a number of suggestions: faults, defects, flaws, weak points, discontinuity, a break or a fracture, a fissure, a crack, a gap, and even the seamy side, which I think has sociological implications, but of course also has geotechnical implications in relation to clay seams in rocks. And in fact, I'll be talking about that in a few minutes. And basically, the tenor of my talk is perhaps encapsulated in this extract from a poem by the Russian poet Konstantinov, who says, "If a building collapses in ruins, what does it matter that it was built after a talented plan?" In other words, no matter how wonderful our analysis and our design is, if it does not take account of the realities, then we can finish up in ruins. This is a rather nice diagram that I've taken from Professor Göran Salfors of Sweden. And Salfors looks at the process of idealization, going from the future structure which we hope to design and build through a process of idealization, which means developing a model of the structure, of the foundation, of the soil, and then assigning material properties to it, putting that through some sort of mathematical or analytical process, and then coming up with a prediction and a design. And I want to focus on the top right-hand corner, the process of idealization and the influence of that on the behaviour of the pile. Now, there are, of course, a number of important steps in developing the schematic model for our design or analysis. The first of those is, of course, to represent the site geology, and that's of prime importance. The second is then, having recognised the origin, the geological origin of our site, to try and represent it in some sort of simplified form so that we can analyse it. Then, of course, we have to assign parameters, geotechnical and possibly structural parameters, to our model. And then we have to also bear in mind some of the real behaviour aspects. The fact that soil, of course, is non-linear. The pile itself may be non-linear. The soil will be layered and not a nice uniform soil deposit. And we may get loading of the piles not only by structural loading directly, but also by the action of ground movements on those piles. So I'm going to look at three sources of imperfections affecting the model, the realities of life: natural geological sources, imperfections created by having inadequate investigation, and thirdly, construction-related imperfections. And in relation to the first, again, Terzaghi, who is, I find, eminently quotable on many things, says, "The earth in its natural state is never uniform. Unfortunately, in practice, clear and simple soil conditions are rather uncommon." And this, of course, is in conflict with the way that we tend to teach soil mechanics and the way that some people tend to practice it. And here's a nice example of a Swedish profile, geotechnical profile, where I would think that a homogeneous elastic isotropic mass may not be a particularly good representation of that situation. Nor indeed of this sort of situation from Greece, where you find the seismic action of the past has led to rather extreme variability in the rock and therefore in the soil deposits that follow from that. Inadequate investigation. This is unfortunately more common than it should be. And I've just shown here a hypothetical situation where we tend to, of course, try and minimise the number of boreholes because we are always under pressure to reduce the cost of this investigation, although we as geotechnical engineers recognise the folly of this, but unfortunately can't transmit it to the people that pay the bills. So here's a situation where we drill 2 boreholes, we find a stiff stratum, we think that's good, and then we go away and we draw this simplified representation of that site. And unfortunately, as you can see here, what we may miss is the fact that the soil layer, the compressible soil layer, is not uniform in thickness, and below that stiff stratum is something that's compressible. So an insufficient number of boreholes or an insufficient depth of investigation can of course lead to inaccurate ground characterisation, and that clearly has consequences on the foundation behaviour. And again, Terzaghi gives us a nice quote. He says, if the subsoil conditions have been misjudged, for instance, on account of inadequate sampling operations, erroneous interpolation between boreholes, or lack of care in the examination of the soil samples, the difference between anticipated and real settlement can be distressingly important. And then, of course, we have construction-related imperfections, and these can arise no matter what method of installation is used for the piles. The diagram on the left, I believe, is actually from round this area. Somebody gave this to me many years ago, and I thought it was rather a nice one, and I show it to you now. The situation where you keep driving the pile and you think, oh, it's going deeper than I thought, and in fact the pile itself is simply squashing. And then, of course, there's the infamous diagram on the right, which many of you will have seen, where the pile driving process on the other side of the road seemed to be taking far longer and the pile was going far deeper, they thought, but in fact the pile had changed direction because of its lateral instability and finished up jacking the car on the left-hand side up. So these are some of the imperfections that arise from reality, and of course we have a similar set of imperfections which are related to the construction of drill shafts. Now, if we're going to look at the effect of some of these imperfections, then we need to have methods of soil structure interaction analysis, because ultimately the behaviour of piles is a problem of soil structure interaction. And so in what I'm going to describe to you tonight, I've used a number of tools. I use tools as I see fit. I don't sort of have a single tool that I use for everything. So you'll see I've used finite element analyses to understand the mechanisms of behaviour in some cases and to look at ultimate capacities. I've used boundary element analyses to look at settlement and lateral deflection problems. And in those methods, we've also had to incorporate the means of analysing so-called free field soil movements. These are soil movements that arise from some source other than direct loading but may impact and load the piles. With respect to those sorts of analyses incorporating ground movements, there are really two ways that you can go about this. The first is that you can use a single analysis where you model the pile, the soil, the loading and the source of ground movement as one, which gives you a complete solution, but that can be time-consuming, particularly in three-dimensional problems. The method that I tend to favour, because it's more efficient, is a two-stage or substructuring approach where we compute or take in some way the free field soil movements that occur, for example, due to reclamation or due to embankment construction, and then we use those calculated soil movements in a soil structure interaction analysis to find out how the pile responds. And that generally is rather rapid and efficient and very suitable for parametric studies. These are the geological sources that I'm going to touch on fairly briefly. Four problems. One is the seamy side, a clay seam below a rock socket. The second deals with strata of variable thickness. The third, a compressible stratum under the pile tips. And the fourth is the situation where we may encounter a boulder below our pile. Looking firstly at the effect of thin seams, which is of course a geological imperfection, the analysis approach that has been adopted here is firstly to look at the pile tip and do a finite element analysis to see what influence that clay seam has on the stiffness and capacity of the tip itself. The second stage then is to take those results and put them into an overall pile soil interaction analysis to see how the overall load settlement behaviour of the pile is affected, and then we can go that one step further and look at group interaction effects. So here's the basic problem. We have the pile tip, diameter D, we have a rock, and at some distance ZS below the pile tip we have this clay seam which is of a particular thickness TS. And if we use our finite element analysis, and this is done with the program Plaxis, commercially available, this is the situation firstly if we have no clay seam. And you see we have this sort of pattern of displacement which gives us a reasonable idea of the mechanism of behaviour and of failure. Now if we have a clay seam and it's reasonably soft, what you see of course is that that weaker seam provides a path for failure of the soil mass or the geotechnical mass. And one would therefore expect that the behaviour of the pile tip with that clay seam will be rather different from that without the clay seam. And indeed that is the case. This is a load settlement plot, load on the vertical axis, settlement on the horizontal axis. The steep orange curve is the case without a clay seam. The red curve is the case with the clay seam. So in this particular case, there's been a dramatic reduction both in stiffness and certainly in capacity of that pile tip. And if we look more generally at this problem, we can express the effects of clay seams on the behaviour of the pile base by means of factors, reduction factors. One for the effect of the seam on base capacity, which is CBS, which has nothing to do with the network, but is the base capacity with the clay seam divided by the base capacity without the clay seam. And then we have the same sort of parameter looking at the reduction in stiffness of the base with the seam to that without the seam. Now we can generate with this finite element approach a series of parametric studies, and here's one. The upper diagram here shows the base stiffness reduction factor on the vertical axis, and that's a log scale plotted as a function of the relative thickness of the clay seam, and the different lines represent the depth of that clay seam below the base of the pile. And what you see, of course, is what you might expect, that the thicker the clay seam, the worse the situation is, the more reduction in stiffness you get, and the closer the clay seam is to the pile tip, the greater is the reduction in stiffness. The lower diagram looks at capacity reduction, and the same sort of principles apply. The thicker the seam, the closer it is to the pile tip, the more effect it will have in reducing capacity, and that's not a surprise. We can compare those theoretical studies with design recommendations, and here is one set of design recommendations which show the dashed lines here, the vertical steps, show the bounds that we use in Sydney for the local sandstone, which is classified in terms of the imperfections, the seams, the thickness and the nature of the seams that are present. And what you can see there is that if you compare those curves, and these are capacity reduction factors on the vertical axis versus thickness of seam, you see that the design recommendations line up reasonably well with the theoretical solutions for a seam which is fairly close to the pile tip. However, if you have a seam such as the upper line, where the depth is, let's say, 0.8 of the diameter, the depth to the seam is 0.8 of the diameter, then the effects are much less than the design recommendations would suggest. So basically, these recommendations, and there are similar ones that are used by the Canadians in their Foundation Engineering Manual, they're generally on the ball or conservative, certainly conservative if the location of the seam is well below the pile tip. The next stage then is that we can look at what happens to the pile itself, because so far we've only been looking at the effect on the pile tip. Now, here is then a typical situation. We have a pile which, of course, has shaft capacity and stiffness as well as base capacity and stiffness. And so we can go through a complete analysis looking at how that situation behaves, and we can compare the overall capacity and the stiffness of the pile, the shaft and the base now, as a function of the clay seam. So on the left-hand side, you have the ratio of the capacity of the pile with a clay seam to that without a clay seam, and on the horizontal axis is the length to diameter ratio of the pile. So when the length to diameter ratio is 0, which means that you only have the pile tip, we have the results for the tip alone. But as, of course, the pile gets longer and you carry more load on the shaft, the imperfections that influence the pile tip so dramatically become less important for the whole pile. And by the time you've got to 20 diameters length of pile, even the most severe effect is damped down. So you have only 10, 15, maybe 20% effect on capacity and stiffness. And in general, the greater the amount of load is carried by the shaft, obviously the less is the effect of the clay seam on pile capacity and settlement. And that has a corollary, and that is that the stiffer the soil is along the shaft, or the more slender a pile, and both of those tend to enhance the amount of load carried by the pile shaft, the less important is the clay seam. Now, I have no detailed results here because of time, but if we look at the effects on a group of piles, it turns out that they can be a little more affected than a single pile for two reasons. One is that if you look at a group of piles and idealise it, if you like, as an equivalent block, then the clay seam will be relatively closer to the base of the group than it will for a single pile. And secondly, again from the mechanics of pile-soil interaction, it turns out that if you have a group of piles, you tend to get more load carried by the base than you do with a single pile. So both of those factors will work towards the seam being rather more important from the point of view of a group than for a single pile. The second imperfection, geological imperfection I want to discuss rather briefly, is what happens if we found piles on a layer of variable thickness. And the possible effects here are firstly that if you have piles of different length or stiffness, or in fact the founding conditions vary, then the pile group subjected to vertical load, instead of going down vertically, will also tend to rotate. And that will give rise to a lateral response, which we may or may not have thought about. Another interesting aspect, and one that I encountered last year in a project in Hong Kong, is that if you have layers of uneven thickness, particularly if you have a layer which increases with thickness, when you do a reclamation or a filling on that site, we normally expect that reclamation is a one-dimensional process. But in fact, when you have layers of variable thickness, you also get, because of that, lateral deformations. And if you've got piles in the vicinity of that reclamation, then those lateral ground movements can interact with the piles and give you effects that you didn't expect. And there's this example in Hong Kong, which I'm not at liberty to tell you too much about, but it was a 26-storey building founded on 144 steel H piles on a reclaimed area, and there were large settlements adjacent to the building, which were expected because it's soft clay below there, and then you get into better material. But what was not expected was the extent of lateral movements near the building, due to the fact that the ground was not horizontally stratified, but we had a thickening of the compressible clay layer. And what happened because of that was that cracks developed in the pile cap, and in fact some of the piles were indeed detached from the cap. And these are just a couple of pictures. The left-hand side shows you the sort of differential settlement you get between the building, which is supported on piles, and the ground, which is settling. But you see on the right-hand side a rather ugly crack in the pile cap, and that we attributed to the fact that the lateral ground movements were sufficiently large that they basically caused the piles to yield at the top and to rotate, and therefore to crack that unreinforced pile cap. The next case I want to look at, again fairly briefly, and is what happens when you have an underlying compressible layer. And in the written version of this paper, I'll include some studies, parametric studies, theoretical analyses to try and give some indication of that effect. But to illustrate the significance of this particular situation, one that I've encountered rather more frequently than I would hope, I've used the case history described by Golder and Osler in the Canadian Geotechnical Journal in 1968. And they were describing the foundation design and performance of a blast furnace foundation founded on a series of piles, and the soil profile is shown here, and the piles were actually founded in a fairly compact, dense, fine sand. And below that, unfortunately, was a layer of leader clay, which, although it's described as firm and silty, is actually quite compressible. What happened here was that pile tests were carried out on a single pile, and they showed a settlement of about 1 millimetre or so. The designers said, fine, that looks good, we'll allow for group effects, so they got their estimate of settlement of 3 to 6 millimetres. And what unfortunately happened was that in the subsequent 14 or 15 years, they got settlements of up to 70 or so millimetres. And of that 70 or so millimetres, 65 millimetres was attributed to the compression of the underlying leader clay. Now, that leader clay was sufficiently far below a single pile not to influence the pile load test. But a group of piles, a large group of piles such as we had here, was certainly sufficient to influence that compressible underlying layer. So clearly we have lessons from this very nice case history. Don't use single pile load test data to predict group settlements without proper ground characterisation. And secondly, obviously, compressible underlying layers can cause substantial increases in settlement, particularly of a group of piles. The final imperfection I want to discuss in this category is the effects of a boulder. And I became interested in this again last year because we had a problem with a project, a very high-profile project on the Gold Coast in Queensland in Australia, where some piles had been jacked into the ground, and everything looked fine from the jacking record, but when they came to do a static load test on those piles that had been jacked, apparently successfully, they got a static capacity which was only about 50 to 60% of the force that was required to jack the piles in. And the question was, why was this so? Well, it turned out that in this particular area there had been an old revetment for a canal, so that involved boulders, and so subsequent investigation showed that there were a number of boulders. Now, this slide I'm showing you is courtesy of Dr. Nussbaumer from the Zublin company in Germany, and it's not to do with the project that I'm mentioning, but It just shows the sort of situation that you can find, that boreholes will not indicate boulders, and then you come to do construction and you see what they unearthed, an extremely large boulder that the investigation had passed by. So again, it's important that you understand the geological origins of the site, because if you're in a glacial situation, then it's not impossible that boulders will lurk below the surface. Because of this project and the mystery surrounding it, we did a little bit of modelling of what might happen, and this is an idealised representation of that imperfection, the boulder. But what happens here is that when you do an initial loading, as in simulating jacking, the boulder becomes part of the pile during the jacking process, and in fact becomes an enlarged base. Now when you then stop jacking, you've got down to where you think you've got the right capacity, then you unload the pile. But unfortunately what happens is the pile then stops being attached to the boulder, and when you reload, you generate skin friction on the pile, but when that skin friction is fully mobilised, you have a gap left between the tip of the pile and the boulder, and it looks as though the pile has actually failed until you push the pile far enough to recontact the boulder again. And that's what this little exercise simulates. So if you took that little kick in the reloading curve as your static capacity, then indeed you would get what we found in reality, that apparently the static capacity was only half to 60% of what we thought. But I think the explanation is the presence of that boulder. And so if we look at just summarising the main features of this sort of situation, you get increased resistance during installation, then on load release, detachment of the shaft from the boulder, and then a smaller apparent resistance and stiffness of the pile until the shaft recontacts the boulder. That's when you start to reload. And obviously the effects again are more pronounced on relatively short piles where most of the resistance is from end bearing, which is the case we had in Queensland. I now want to talk about construction imperfections, and we almost invariably idealise a pile as a nice uniform diameter or size cylinder, vertical cylinder, as shown on the right-hand side. The harsh realities of life are that sometimes you have a non-ideal situation. You can have imperfections caused by the construction process which result in necking or voids of in the pile, and these are what I would term structural imperfections. And of course you may also have what I term geotechnical imperfections, which is debris left at the base of the pile due to inadequate cleaning operations, and that's the so-called soft toe situation. So that's a geotechnical imperfection. Now, if we are interested in looking at what the consequences may be of these construction-induced imperfections, then looking firstly at structural defects, we can treat defects as pile elements of different diameter, stiffness and strength, and we can do some sort of analysis, pile-soil interaction analysis, to examine the effects of those imperfections on stiffness and on capacity. And here's, again, a hypothetical example, but I think it illustrates what might happen. So on the vertical axis, we have applied load as a percentage of the ultimate capacity. On the horizontal axis, we have the settlement, and the full line shown on the left is the ideal situation where you have no defects. The dashed lines represent an analysis taking into account the defect, and this is a fairly massive defect. It's a necking of the pile over 40% of the length of the pile, which you may think is pretty terrible, and indeed it is, but it is not entirely unknown. Now, depending on the structural strength of that imperfection, you will get a break-off, and a rather sudden break-off, theoretically, of the load settlement curve when the stress in that imperfection reaches the ultimate stress of that imperfection. And if you have a fairly weak pile, then of course you get a structural failure of the pile well below the geotechnical capacity of the pile. And okay, you may think that that's theoretical, but indeed it's also borne out in reality. Here is a pile load test reported by Abdrabo in 1997, which shows a load settlement curve which looks pretty good until it gets to about 1,200 kilonewtons, and then you get abrupt failure. And when they exhumed that pile, they did indeed find that there were structural defects which caused that failure. So structural defects have the capacity, if I can use that confusing word, have the ability to reduce or cause very sudden failure and reduce the overall capacity of the pile. Now again, if we want to generalise this, we can look theoretically at introducing some measure of integrity, and I've chosen what I've call here a structural integrity factor, which is basically the modulus times the area divided by the length of the defective part of the pile divided by the modulus area divided by length of the intact pile. If there is no imperfection, then this structural integrity factor is infinity. That's good. So big is good in this case. And we can relate that theoretically to a head stiffness reduction factor which describes the increase in settlement or the reduction in stiffness of the defective pile as a fraction of the intact pile. And what I have here on the vertical axis is a plot of the head stiffness reduction factor. Remember, that's the stiffness of the pile with the defect, or that without the defect, plotted against the structural integrity factor. And if you have high values of that structural integrity factor, obviously the reduction factor is 1, which means there's no effect. But if you get low values, in other words, you have rather severe defects, then theoretically you have, depending on the depth of that imperfection, you have quite a significant reduction in stiffness of the pile and, of course, potentially of capacity. You'll also see some yellow dots on that diagram, and these are experimental data from model tests that were carried out by Dr. Kenneth Zhu, a former PhD student of mine, which are reasonably consistent with the theoretical predictions of the reduction in stiffness because of those structural defects. Now, again, that deals with single piles, and the question is, what happens then if you have one or more defective piles within a group of piles? And I don't have time to discuss this in detail, but generally what happens is, clearly, if you have defective elements within a system, then you will have additional settlements, but you will also generate non-uniformity of axial loads, because the loads will tend to be shed from the less stiff components to the stiffer components. There will be a tendency for lateral deflections because you have uneven support conditions. You will get cap rotation. You may get additional bending moments then in the piles, and the piles, unfortunately, are frequently not designed to carry significant moment, and so you may actually get a structural yielding of the pile near the pile cap connection. And so the effects of defects on groups are rather similar to the effects of piles of varying length. And indeed, anything that gives you an unevenness of support, whether it's defects or whether it's a different stiffness of material that you're founding on, or varying thickness of soil, all of those will tend to give you similar effects. Now, looking at the geotechnical defects, the soft toe that may arise from inadequate cleaning gives you, again, fairly obvious effects. Certainly a reduction in stiffness of the base, which in turn causes a reduction in the stiffness of the pile head, increase in settlement, and that tends to be more severe after the shaft friction is mobilised. And also, those soft toes lead to an apparent reduction in the pile capacity, in that, as you will see, you get what looks to be failure of the pile. But in fact, because the soft material at the base of the toe is generally confined, you don't actually get failure as such. You keep squeezing and squishing the material until you get it to a stage where it can no longer do that. And you may still have the ultimate capacity of the pile tip available to you, but only after extremely large settlements. There's some very nice data that's been published by Dr. Zachi Mo and Dr. Wu in Taiwan, and I've just taken a couple of their cases here, showing on the vertical axis the pile tip settlement and on the horizontal axis, in this case the load on the pile tip. A clean base pile A is shown dashed there, and it's a nice healthy pile. A pile with 25 centimetres, that's 10 inches of thick slime at the base, looks to be much inferior. It settles more and it does not appear to have the same sort of capacity, although I guess if you load it far enough, it may have the same capacity. Now, how can we treat this sort of problem? Well, we found that you can in fact treat the soft toe as a compressible element of the pile. So you add just a little squishy element to the bottom of the pile and treat it as a pile. And that reproduces the main features of greatly increased settlement once the shaft resistance is mobilised. And indeed it gives you rather similar results to a finite element large strain analysis. And just to show you some comparisons between this rather simple-minded approach of just treating the soft toe as a compressible pile element. Again, these are the tests of Wu and Mo, and there are two piles here. One is the full dots here, which are the pile that's been properly cleaned, and you see the full line is the calculation, which matches it well. The dashed line and the triangular elements there represent a pile with 1.5 metres of debris at the base, which is rather extreme. But you see that once you mobilise the full skin friction, then that base really takes off in terms of settlement. So this simplified approach seems to work well for that case. I just now want to describe in a little more detail the situation that we had in Hong Kong 2 or 3 years ago, where there were two high-rise housing blocks that exhibited uneven settlement. And as I'll show you, subsequent coring of the piles revealed that the piles were not what they should be, that the piles were short or not properly founded. And so analyses were carried out as part of a prolonged legal process to assess the risks of proceeding with construction and of underpinning the buildings. Now, this is taken from the front page of a local newspaper in Hong Kong in the year 2000, and the blocks circled in red are the two blocks in question. They had reached level 34 of 41 levels, and you'll see a typical Hong Kong situation, a very high density of construction. These two blocks were in very close proximity, about 5 metres away from a secondary school, a 6-storey secondary school shown in white at the bottom there. And this, of course, gave considerable concern to everybody because the buildings were in fact leaning towards the school. Now, when we looked at this, again, we looked at the geotechnical conditions. The piles were supposed to be founded in that lowermost slightly weathered rock stratum, above which was extremely weathered rock and then more compressible materials. But basically, the foundation was meant to be in that slightly weathered rock at the bottom of that profile. Here is a plan of the two buildings. Each was supported on 18 board piles, drill shafts, 2.3 metre shaft diameter, belled out nominally, but I think in reality they weren't, to 3.8 metres, and designed as end-bearing piles. So these were, and they were supposed to go down 30 to 40 metres onto that slightly weathered rock. These are settlement measurements, just a few of the settlement measurements that were made on one of those blocks. The blocks were called Block D and Block E. And settlement measurements were started only when the buildings had reached the 17th floor, because there had been, just prior to that, a revelation in Hong Kong that the founding conditions for some of the pile foundations were not what they should have been. And so the Housing Authority set up a process of measurement. And we had expected, or we would expect, a uniform settlement of the order of 15 to 20 millimetres under full dead loading if everything was right with these foundations. Indeed, what we got was a differential settlement of the order of 30 to 40 millimetres in this block over the period when we went from level 17 to level 34. At that stage, which was a very bad new year for the people involved, the 1st of January 2000, investigative coring was started to try and identify what the founding conditions were for all of these piles. And you'll see that during that period of investigative coring, which went over about 6 to 7 weeks, there were in fact additional settlements induced because of the coring process, and I'll come back to that in a little while. This is, again, from the Hong Kong newspaper, a model representation of the findings of this coring. The grey bits are the good bits of pile. The yellow bits represent the shortness of the pile from the supposed founding level, and the blue bits, particularly on Block D, represent drilling fluid or something extremely soft. So what you can see there is a lot of those piles were not to the level that they should have been. And if we look in a little more detail, the green dots here represent the piles that were as recorded on the sheets. The pink dots represent, for this block, the piles that were up to 10 metres short of where they were supposed to be, the red piles up to 20 metres short of where they were supposed to be. And here's the other block. Again, this was, if anything, a little worse, that we had 6 or so piles that were up to 20 metres shorter than they should have been, and all, unfortunately, on the one side. In analysing the possible scenarios and what the consequences of these imperfections were, and these were essentially imperfections of construction and imperfections of integrity on the part of the piling contractor. We used a program that we developed called PIGS, Pile Group Settlement, which takes account of different pile types within a group. The effects of a soft toe and variable pile length can be considered. We can use a different model for each pile, which we were able to do here, and it allows for both the settlement and rotation of the pile group. And it also incorporates ground movements due to the drilling process, which, as I showed you, were up to 30 millimetres, input as external soil movements. And we managed to calibrate our analysis with the measured settlement profile. So these, you see there are 3 different sections that we looked at, and these are the settlement profiles across those sections. The dots are measured, the hashed lines are calculated. So we managed to calibrate the model reasonably well to the measurements. The reason that we did that was that we wanted to look at possible scenarios in how to cope with this problem. And the conclusions that we reached from the analysis and from this case generally were that the uneven settlement of the buildings could be explained by the presence of piles with soft toes, with inferior founding conditions, and with shorter shafts than designed. There was considerable concern at the time over the fact that the drilling process itself caused additional movements, and there was a concern that if there were to be remedial piling done, as you would have to do to boost up the pile foundation, that drilling could cause additional settlements and endanger the integrity of the whole building. There were a number of alternatives looked at. The installation of additional piles to stiffen up the low side, if I might call it, of the foundation, but there was a recognition that there were significant risks involved in installation. Now, what of course you have to recognise is that we are drilling in ground that is stressed by a 34-storey building, so it's highly stressed, and so disturbing the ground is much different to drilling a hole in open ground. There was an option for partial demolition to use the existing piles up to the capacity that it was felt was safe, and to have, in the midst of this 41-storey forest of buildings, 2 13-storey buildings. I think you could imagine that sociological and other considerations would deem that not to be a good option. And complete demolition was another option, and indeed that was the last option that was looked at and the one that was adopted. And so these 2 buildings no longer exist, they're demolished, and because of the concerns that the locals have about that site, bad feng shui, there will be no new buildings on that site. And this leads into a more general discussion of how we cope with the consequences of imperfections. And there are issues related to, firstly, the investigation, and secondly, to the design. And I won't have time to go into detail on these. One could sort of talk about this at length. But certainly, simply to say that you need to take care to avoid additional disturbance and settlement when you are either doing investigations or remedial foundation work under a heavily loaded building. And this is by no means the only building that I've had experience with that has settled due to investigation or remedial drilling. SPT testing has to be done carefully because the whole process of doing SPTs has to be very, very carefully controlled. It's not a process that you can abuse. And you need to have, of course, balanced fluid pressures in the drill holes or the cores. In terms of design, we may need to correct the settlement of a building that has tilted because of some imperfection. We may need to design remedial or enhancement works, and in that design we may need to try and control and engineer the sharing of load between old and new elements. I'll just very briefly run through some of the methods of correction of settlement because they have in fact been used, again in Hong Kong. There are 2 classes, one that I call hard methods, which involve actually getting into the foundation system and interfering with it. And so the hard methods may include anchor stressing, so you actually pull the foundation down with anchors, additional loading of parts of the building to get it to settle more, cutting of the piles, jetting of the soil below the pile tips, jacking of the foundation on the low side, or fracture grouting. All of these have been proposed. Some of these have actually been used. And in fact, we used the pile cutting process as one of 3 processes on another job, not the one I just described, but on another job for correcting the tilt of 2 completed buildings. And the interesting thing, and I won't go into detail on that, but you can, that is a pile that has been exhumed below the pile cap and then cut by a process which is fairly tender. And the interesting thing was that we cut 41 piles of the 298 piles, and we caused only a settlement of 5 millimetres on the high side. So although some people think that if you've got one bad pile in your foundation it's disaster, we actually cut almost 20%, or well, less 15% of the piles in that foundation, and nothing particularly terrible happened. There are another class of methods which I call soft methods, which I really like because they're methods that don't intrude on the foundation but get nature to work for you. Soil extraction is one, and we know of that, of course, from the Tower of Pisa, which was a magnificent restoration. Dewatering, causing additional settlement by groundwater removal, is a possible means, although I am often nervous about that because dewatering is not a process that you can control precisely, and you do need precise control. Compensation grouting to sort of jack up low bits is a possibility, as long as you don't then cause a subsequent settlement, because when you jack up, you also jack down on what's below, and action and reaction have to support each other. And there's another approach called the removal of soil support, which is a method that we developed and we hoped it would be used, but they got cold feet. But this is a soil extraction process, and indeed it's been used, let me say, well before its successful use on the Pisa Tower. Amir Soleimani from Iran has described a couple of cases where they've corrected the settlement of a tall grain elevator by means of cutting horizontal slices of soil away with a chainsaw, basically. And here's another process, I think, that was used on the right-hand side in the Pisa Tower. The RSS removal of soil support approach, the concept there is that you drill holes outside the footprint of the building and allow the soil to settle, and the settling soil will carry the piles with them, and if you're lucky, you will get a controlled settlement. And of course you can use and would use the observational method to make sure that you got the required results. Now that means that you don't actually intrude on the foundations, but you use the soil to do the work for you. And my colleague at the Hong Kong University of Science and Technology, Charles Ng, did some pilot centrifuge tests. Now, these were not with piles, this was just with a shallow footing, but just to try and see whether the process of drilling holes outside the footprint of a loaded, tilted footing would work. And so here's his centrifuge set up, and he had a footing which he had originally tilted at 1 in 27. And then he got his clever little robot to drill a series of holes, firstly staggered, and then he came back and filled in between. And what this shows on the vertical axis is the tilt of the building in percent versus the sequence of drilling of the holes, going from number 1 to number 9 holes. And what happened was that drilling 9 holes outside the footprint of that loaded foundation caused the tilt to correct from 1 in 27 to 1 in 67. So I think that's a process that I think has some potential for remedial work. Now, just very quickly, and I will perhaps skip a little bit of this, foundation enhancement works. It may also be necessary not only to correct the settlement, but also to boost the foundation capacity and stiffness. And one can try and do that if you know that you have defective piles. You can try and repair the piles themselves, or you can extend the pile cap to strengthen or stiffen the foundation, or you can add new piles to, again, strengthen or stiffen the foundation. Now, enhancement work on piles, repairs, you can use structural repairs if you know that you have structural defects, and if you have geotechnical defects, you can attempt to grout the base. And this has become, in some places, particularly in Bangkok, a fairly standard approach to the construction of board piles, that they sort of would preview that the piles may need base grouting, and so they do it beforehand. And this is just a diagram again from Dr. Mo showing the difference between base grouted piles, load settlement behaviour with the full lines, and ungrouted piles, just showing that grouting the base of the pile can result in substantial improvement in performance. Now here is another example again from Hong Kong showing a situation where again, the board piles were supposed to go down to the brown layer, grade 2 rock, and coring indicated that they in fact only went to an inferior grade of rock. They were shorter, and so there was then remedial action done. Additional piles were added to stiffen up the foundation system. And what we did here was to look at the performance of the upgraded foundation. And to do this, you need an analysis which can alter the foundation system during the loading process, because you are adding piles after the loading has started. You need to consider piles of different characteristics, because generally your new piles will be different to the old. You need to consider nonlinear behaviour of piles, and you need to be able to consider defects in the piles. The other thing that is important is that you should look at the distribution of load between the existing foundation system and the new foundation system. If you're putting in a foundation system that is a lot stiffer than the existing system, then that will tend to attract the early incremental load. But you can control the way that the load is shared between the new and the old systems by using this sort of system of controlled stiffness inserts. And these are simply inserts, and they can be neoprene, rubber, some compressible material that you put between the pile head and the pile cap, and you can work out what stiffness you require in order to get that overall cap plus insert plus pile system to have the required stiffness so that it settles and therefore distributes the load in the way that you want. And this is, and I won't go into detail, but it's a very simple way of calculating the stiffness of the insert that you require in order to get the performance that you require. You can't have much more simple equation than that. This is the calculated load settlement curves, load vertical axis, settlement horizontal axis for 4 situations. The full line here is the as-designed case, and this was to be a high-capacity pile with up to 250 meganewtons. That's quite a large load as ultimate. The lowermost line is the calculated load settlement curve with the defects in there, in other words, with the inferior founding conditions. And clearly the working load here was about 80 meganewtons, so that pile would have failed before it got to working load. When this problem was detected, there was about 20 meganewtons on this particular pile. And so what you see then is the calculated load settlement curves after 16 additional piles had been added to this system. And what you find is that, of course, you get an immediate increase in stiffness, and you finish up restoring the capacity pretty close to what it should have been in the first place. The other thing that I point out is that there are 2 lines in the middle. One is where you don't use stiffness inserts, that's the left-hand line. The other one on the right-hand side is where you do use stiffness inserts. Now, the beauty of using inserts is that you can control the load distribution, and these blue lines show the load distribution in various new piles without inserts, and you see quite a non-uniformity of load. The purple lines on the right-hand side represent in those same piles the loads calculated with the stiffness inserts in place, and now they're essentially uniform. And in a place like Hong Kong, where design is dictated by the load in individual piles, to be able to have uniformity of load is a much more efficient design. So, additional piles obviously can restore the performance of a defective pile. The load distribution in remedial piles, of course, is generally non-uniform, but you can achieve or head towards uniformity by the use of these control stiffness inserts. And that's of particular advantage if your design, as it is in Hong Kong, is controlled by the maximum pile loads. So just in conclusion, just a few observations. Firstly, in terms of imperfections, the world is imperfect, and imperfections that relate to piles can create unforeseen problems for designers. The significance of those imperfections clearly depends on their nature and extent, but I think we should develop at least a mild form of atelophobia, which is the fear of imperfections. We should be looking for them. We shouldn't assume that because we as designers draw a nice uniform pile, we draw horizontal lines to represent the soil profile, we shouldn't assume that nature is so obliging. The important natural imperfections that I've considered, and these are but a few of many, are clay seams below the pile toe, compressible layers below the founding levels, compressible soils of uneven thickness, and differences in founding conditions, for example, due to boulders. And in general, anything that gives us a variable founding condition will tend to lead to differential settlements within the group, to lateral movements, to head rotations, to induced bending moments in the pile heads, even under purely axial loading. So you need to be very careful. If the pile contractor says, do I really need to put reinforcement at the top of the pile? There's not very much lateral load. You probably need to allow for these sorts of imperfections. In terms of construction-related imperfections, structural imperfections, the pile capacity depends on the strength of that defective section, and failure can be sudden. You may have little or no warning, and then the pile just goes bang. And there may be also some reduction in head stiffness. With geotechnical imperfections, the result is generally more gradual. You don't have this sort of sudden failure. You have what appears to be a much softer behaviour, and again, that will depend on how much of the load is carried by the base. In coping with imperfections, we need to take great care in investigation. I think this is, to me, this is something that people have perhaps overlooked. The fact that when you do investigations, that you are disturbing what is usually highly stressed ground, and there are consequences. Ground movements may be induced, and they may in fact interact with the existing foundation which you're trying to preserve, and it may be counterproductive. And in terms of correcting uneven settlements, I think you have hard and soft methods available. And again, you need to be very careful with remedial piling that your side effects don't cause a problem. In terms of designing enhancement works, it's a challenging analysis problem because you have a situation where the system changes during the loading process. You can control and design the remedial system to have the load distribution that you want. It is not a difficult process, and it has been used in Hong Kong quite successfully, and it can be important where your design criteria involves limiting loads on individual piles. This is the cover page of Terzaghi's famous Theoretical Soil Mechanics, published in 1943. This is the book that I had to try and read as an undergraduate. This is the book that I had difficulty in understanding. But this is the book that intrigued me about geotechnical engineering and soil mechanics as it was known then. The uncertainty of it all. And I think, again, it's encapsulated in this quote by Terzaghi. If the engineer is fully aware of the uncertainties involved in the fundamental assumptions of his computations, he's able to anticipate the nature and the importance of the differences which may exist between reality and his original concept of the situation. So, ladies and gentlemen, I hope that in this lecture I have perhaps assisted you to understand a little better the importance of those differences arising because of the realities and the imperfections of real life. Thank you very much.
Thank you, Professor Poulos, for again reminding us of the importance of understanding the fundamentals and how nature can play games with those fundamentals. We do have a couple of minutes, and I was wondering if you might want to answer a few questions if the audience has some questions to ask. Are there any questions? Well, seeing none, I wanted to present you with a gift, a special gift, in addition to the other gifts that you received, and we're going to send it to your home because it is a copy of what we consider to be our coffee table book because it can serve as a coffee table, actually. It's it's a collection of 78 papers which have been published over the last 150 years, geotechnical papers by ASCE. And it's a landmark edition, and it'll go nicely, I think, in your library. So again, thank you very much.
Thank you very much.
With that, we will adjourn, and we hope to see each of you coming up to the GeoFrontiers in Austin in January. And so with that, adjourn.